Have you ever wondered what the future of computers looks like? Scientists and engineers are building something entirely new: quantum computers. These aren't just faster versions of your laptop. They work in a fundamentally different way, using the strange rules of quantum mechanics to solve problems even supercomputers can't handle. This could revolutionize everything from medicine to materials science. But here's the twist: there's more than one way to build a quantum computer. Think of it like cars. Some run on petrol, some on electricity. In quantum computing, the engine is called a qubit. Unlike a regular bit, a qubit can be both 0 and 1 at the same time, thanks to superposition. Different teams are racing to build the best qubits. Two leading contenders: superconducting qubits and trapped ion qubits. One uses ultra-cold electrical circuits, the other individual atoms held by lasers. Both have unique strengths and challenges. Why does the type of qubit matter? It affects speed, error rates, and how big we can build these machines. We need qubits that are stable, controllable, and scalable. Exploring different options is crucial. We don't know which will win. This friendly competition is driving science forward. The race is on to build the computers of tomorrow. Let's dive into superconducting qubits, a favorite of tech giants like IBM. Imagine a tiny electrical circuit cooled to near absolute zero, where electricity flows with zero resistance, a superconductor. These circuits act as artificial atoms controlled by electrical signals. IBM's Eagle processor uses over 100 superconducting qubits on a single chip, kept ultra-cold in a dilution refrigerator. This extreme cold protects the fragile quantum states. Each qubit is like a tiny pendulum pushed by microwave pulses to represent 0, 1, or both at once. Superposition. By timing these pulses, scientists run complex quantum algorithms. IBM's goal? Scale up, pack more qubits onto chips using techniques from the traditional computer industry. They hope to build quantum computers with millions of qubits. This approach is attractive to big tech because it leverages existing manufacturing know-how. The superconducting path feels like a direct route to powerful quantum machines. The race for scale is on. Now let's explore a different approach: trapped ion quantum computers. Here, scientists use individual atoms, ions, held in place by electric fields inside a vacuum. These ions are nature's perfect qubits, identical and flawless. At Oxford, researchers trap and cool these ions, then control them with microwaves generated right on the chip. It's like giving each atom its own radio station. This method combines atomic precision with microchip engineering. The goal? Link small, powerful modules into a larger quantum computer. Trapped ions can hold quantum information for a long time, called long coherence time. This stability allows for complex, accurate calculations. Trapped ion teams aim for the highest possible accuracy, or fidelity. Their quest is for near-perfect qubits, pushing the limits of what's possible. Perfection, not just scale, is their mission. Superconducting qubits are incredibly fast. Operations take just nanoseconds. This speed means millions of calculations per second, crucial before quantum states fade. Another advantage is scalability. These qubits are built on silicon chips, using established microfabrication techniques. Companies like IBM and Google can leverage decades of chip-making expertise. Strong industry support fuels rapid progress, with billions invested and large engineering teams at work. The solid-state nature of these qubits allows for robust, customizable processor designs. They're physically fixed, making wiring and layout more straightforward. While the environment is complex, the core hardware is familiar territory for engineers. Superconducting qubits are built for speed and scale. But superconducting qubits have a big weakness. They're extremely sensitive. Even tiny disturbances can disrupt their quantum state, causing errors. This is called decoherence. Calculations must be lightning fast before the magic fades. High error rates are a challenge. Manufacturing imperfections mean qubits aren't identical, making calibration tough. Quantum error correction requires many extra qubits, adding complexity. Extreme cooling is another hurdle. Dilution refrigerators are huge, expensive, and power-hungry. Scaling up means even more cooling and wiring challenges. These engineering obstacles make desktop superconducting quantum computers a distant dream. The path to scale is paved with technical hurdles. Trapped ions shine in stability. As perfect atomic qubits, they're beautifully isolated in a vacuum. This gives them coherence times thousands of times longer than superconducting qubits. Their operations are incredibly accurate, over 99.9% fidelity. Fewer errors mean less need for complex error correction. Trapped ions are fully connected. Any qubit can interact with any other, making algorithms more efficient. This all-to-all connectivity is a major advantage. Control is precise. Scientists can target individual ions with lasers or microwaves. The result is a finely tuned instrument, not a wild beast. For reliability and precision, trapped ions set the gold standard. We have two remarkable technologies: superconducting qubits, focused on speed and scale, and trapped ions, aiming for perfection. IBM's approach is to build bigger, faster processors, tackling errors with numbers and correction codes. Oxford's path is to create the best possible qubits, building modular, high-fidelity systems. Both are vital. Superconducting qubits drive rapid scaling and software innovation, while trapped ions set benchmarks for accuracy. The future may blend both fast superconducting processors with stable trapped ion memory. This competition fuels progress and innovation. Ultimately, all teams share one goal: to unlock the quantum realm and build computers that will change our world. The quantum race is just beginning.